You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Vision language models are a class of artificial intelligence systems that integrate both visual and textual information, enabling them to operate across multiple modalities, rather than being restricted to language alone. Traditional language models process text and generate text-based outputs, which makes them powerful for tasks like summarization, translation, or reasoning over written input. Yet so much of the world's knowledge is encoded in visual form, through images, diagrams, photographs, and videos, that text-only systems leave a vast amount of information untapped. Vision language models address this by bringing together the ability to interpret images with the ability to generate and understand text. In effect, they serve as translators between the visual and linguistic worlds, enabling applications that require comprehension of both. Whether it is generating captions for photos, answering questions about a picture, or grounding words to specific objects, these models extend the reach of AI into richer, multimodal domains. The motivation for combining vision and language arises from both practical needs and theoretical opportunities. Human communication is inherently multimodal. We point, gesture, describe, and annotate images with words, blending sight and speech seamlessly. AI systems that remain confined to text cannot fully participate in this type of communication. For example, an assistant that can read legal documents but cannot interpret the charts or tables embedded within them is incomplete. Similarly, a support system that can answer questions about policies but not about diagrams or screenshots is limited. By merging vision and language, AI systems gain a more holistic view of the information landscape. This integration unlocks a range of applications, from helping visually impaired individuals understand images through captions, to enabling content moderation systems to detect unsafe or inappropriate imagery in combination with text. Multimodality thus expands not only what AI can do, but also how naturally it interacts with the human world. Grounding is one of the core tasks in vision language modeling. Grounding refers to aligning words with objects or regions in an image, establishing a correspondence between linguistic expressions and visual elements. For instance, when someone says, "the red ball on the left," a grounded system can point to or highlight the correct object in the visual field. This capability makes language more than abstract. It ties it directly to physical or visual reference. Grounding is essential in tasks like interactive robotics, where instructions must connect to actual objects, or in image editing tools, where textual commands like blur the background must be linked to specific regions of an image. Grounding is what transforms vision language models from passive describers of images into systems that can interact meaningfully with them, providing the foundation for applications that bridge perception and action. Captioning tasks highlight another major capability of these models. Captioning involves generating natural language descriptions of images, effectively telling a story about what is seen. This might mean a simple factual statement, such as, "a dog playing with a ball in the park," or a more elaborate description that includes context, emotion, or interpretation. Captioning is particularly valuable in accessibility, where it allows visually impaired individuals to receive descriptions of photographs, videos, or graphical elements. It is also useful for cataloging digital assets, making large collections of images searchable through natural language queries. Captioning demonstrates how vision language models can transform raw pixels into structured knowledge that humans can consume, share, and use for decision-making. By enabling machines to describe images as humans might, captioning makes visual information more accessible and useful across domains. Visual question answering, or VQA, builds on these capabilities by allowing systems to answer textual questions about visual content. In this task, a user might present an image along with a question like, "What color is the car?" or "How many people are sitting at the table?" The system must interpret both the question and the image, combining language understanding with visual recognition to generate an accurate answer. VQA is a step beyond captioning because it requires reasoning. The system cannot simply describe everything but must extract and report only what the question demands. Applications of VQA range from education, where students can ask questions about diagrams or illustrations, to content moderation, where systems can detect and describe sensitive content. The challenge is not only in recognizing visual elements, but in connecting them with the semantics of the question, requiring genuine multimodal reasoning. The architectures of vision language models reflect this dual nature. Many rely on visual backbones, such as convolutional neural networks or vision transformers, to process images into embeddings, which are compact numerical representations of their features. These embeddings are then integrated with embeddings from language models, often using cross-attention mechanisms that allow the model to align visual and textual information. Some designs treat both modalities symmetrically, feeding images and text into a unified transformer architecture. Others use specialized encoders for each, and then merge their outputs in a joint representation space. These architectures are what enable the cross-modal reasoning required for grounding, captioning, and VQA. The design space continues to evolve, but all share the common principle of creating shared representations that allow information to flow between visual and linguistic domains. Pre-training strategies are crucial to making these models effective. Just as language models are pre-trained on vast amounts of text, vision language models are pre-trained on large datasets of paired image-text data. These pairs might come from captions on social media, descriptions in scientific papers, or annotations in curated datasets. By learning from these pairs, models develop an ability to connect visual features with linguistic descriptions, grounding words in the world of images. Pre-training creates a foundation of multimodal knowledge that can then be fine-tuned for specific tasks, such as generating medical image captions or answering questions about product photos. The scale of pre-training data matters greatly. The more diverse and extensive the image-text pairs, the more robust and flexible the resulting model. Pre-training thus serves as the multimodal equivalent of language immersion, giving the system experience in connecting words and visuals across countless contexts. Contrastive learning methods such as COC-LIP provide another influential approach. Instead of directly generating captions, these systems learn to align images and text by pulling matching pairs closer in the embedding space and pushing non-matching pairs apart. For example, the text "a photo of a cat" and an actual cat image would be pulled together, while that same text paired with a picture of a dog would be pushed apart. This creates a joint embedding space where visual and textual data coexist in meaningful alignment. The power of this approach is its generalization. Once trained, the system can perform zero-shot tasks such as retrieving the right image for a text query or generating labels for unseen images. Contrastive learning demonstrates that vision-language integration does not always require supervised labeling. It can emerge from large-scale pairing and alignment, producing models that are flexible, efficient, and surprisingly capable across diverse domains. The applications of captioning highlight the practical benefits of these technologies. Accessibility is perhaps the most prominent example. Automated captions allow visually impaired users to understand visual content that would otherwise be inaccessible. Beyond accessibility, captioning also serves digital asset management, where large repositories of photos or videos must be tagged for easy retrieval. Captioning can also support creative industries by providing descriptions that help with search, recommendation, or automated editing. Even in everyday contexts, captioning can make personal photo collections searchable, allowing users to find pictures of my dog at the beach without manually labeling images. These applications underscore how captioning transforms unstructured visual data into structured linguistic knowledge, making images not only viewable but also searchable, shareable, and integrable into broader workflows. Applications of VQA extend into numerous domains as well. In education, VQA systems can support learning by answering student questions about diagrams, illustrations, or photographs in textbooks. In content moderation, They can flag images that contain prohibited content and explain what was detected, making moderation more transparent and accountable. VQA can also support knowledge extraction, where systems scan large collections of visual data and answer targeted queries, such as identifying patterns in medical imaging or analyzing satellite photos. Each application relies on the ability of VQA systems to interpret both the visual input and the semantic structure of the question, combining them into meaningful answers. By enabling interactive questioning of visual data, VQA moves beyond static description to active reasoning, giving users a more powerful way to engage with visual information. Evaluation benchmarks ensure that vision language models perform reliably. Datasets such as COCO captions, which test captioning quality, or the VQA dataset, which measures question answering performance, provide standardized challenges for comparing models. These benchmarks assess not only accuracy, but also fluency, coherence, and relevance. However, evaluation remains challenging because multimodal tasks often involve subjective judgments. Two captions may describe the same image differently, yet both may be valid. Similarly, VQA answers may vary in phrasing while still being correct. Evaluation frameworks must therefore be designed to capture this diversity while still rewarding precision. Benchmarks play a critical role in driving progress, highlighting weaknesses, and providing transparency about what models can and cannot do. They ensure that claims of multimodal capability are backed by measurable performance. Bias concerns loom large in vision language systems. Because these models are trained on large image-text datasets scraped from the internet, they risk inheriting and amplifying social biases. For example, captioning systems may reinforce stereotypes by consistently associating certain activities with particular genders or ethnicities. VQA systems may misinterpret images that fall outside the distribution of their training data, leading to biased or unfair outputs. These risks are amplified because outputs often appear authoritative, even when flawed. Addressing bias requires curating datasets more carefully, applying debiasing techniques during training, and monitoring outputs during deployment. Without such efforts, vision language models risk perpetuating inequality rather than democratizing access to information. Bias is not merely a technical flaw but an ethical challenge that must be confronted directly. Limitations in generalization present another challenge. Vision language models perform well on familiar data, but may struggle with unusual or low-resource images. For example, they may handle everyday photographs competently but falter on rare medical imagery, abstract art, or images from underrepresented cultures. This limitation reflects both the biases of training data and the constraints of current architectures. Generalization is particularly difficult in tasks like VQA, where reasoning about unfamiliar contexts requires both visual understanding and linguistic flexibility. Improving generalization requires more diverse training datasets, better architectures, and methods that allow transfer learning across domains. Until then, vision language models must be deployed with caution, particularly in contexts where the cost of error is high. Industrial adoption of vision language models demonstrates their growing maturity. They are now embedded in consumer products such as photo search engines, accessibility tools, and social media captioning systems. Enterprises use them for digital asset tagging, automated content moderation, and even quality assurance in manufacturing. Their integration reflects both demand and practicality. Organizations need systems that can handle the multimodal nature of real-world data. As adoption increases, the need for reliability, fairness, and compliance grows as well. Vision language models are no longer experimental, they are infrastructure. Their role in consumer and enterprise tools marks a turning point in AI, where multimodal capability is no longer a novelty but an expectation. As vision language systems mature, they provide the foundation for document intelligence, where multimodal reasoning extends to structured and semi-structured documents. Invoices, contracts, research papers, and government filings often combine text with diagrams, tables, and images. Understanding these requires the same integration of visual and linguistic cues that underlies captioning, grounding, and VQA. Thus, the evolution from text-only models to vision-language models naturally paves the way for systems capable of handling the rich diversity of real-world documents. This integration is the next step in expanding AI beyond narrow modalities into systems that can reason across the full spectrum of human information. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Grounding extends beyond photographs of everyday objects and scenes. In practice, many of the most valuable applications of vision language models involve diagrams, charts, and other structured visuals that blend text with imagery. Think of a scientific paper where a graph illustrates a relationship between variables, or a corporate report that includes flowcharts describing business processes. In such cases, grounding means linking words or questions not only to objects in pictures, but also to elements in charts or diagrams. When a user asks, "Which bar in this chart represents last quarter's revenue?" the model must align the textual reference with the appropriate region of the chart. This capability turns vision language systems into powerful tools for data literacy, enabling users to query complex visualizations naturally rather than relying on specialized software. Grounding beyond images is essential, because much of the information that professionals rely on is presented in structured visual formats, not just in photos. Fine-tuning is another important method for making vision language models more useful in specific domains. Pre-training on large, general-purpose datasets provides a foundation of multimodal knowledge, but domain-specific tasks often require more tailored expertise. Fine-tuning allows organizations to adapt vision language models to contexts like medical imaging, satellite photo analysis, or industrial quality control. For example, a model fine-tuned on radiology data can generate more accurate captions of X-rays or MRIs, describing abnormalities in language familiar to medical professionals. Fine-tuning also allows organizations to encode domain-specific policies, ensuring that outputs reflect industry standards and avoid misleading phrasing. By investing in fine-tuning, companies transform generic multimodal systems into specialized assistants capable of supporting critical tasks. This practice reflects a broader truth in AI. General intelligence provides the foundation, but targeted adaptation unlocks real-world value. Cross-modal retrieval is a capability that showcases the practical power of joint embeddings in vision language models. By representing images and text in the same numerical space, these models make it possible to search across modalities. A user can type a text query, such as "a mountain at sunset," and retrieve relevant images, or present an image and receive related textual descriptions. This two-way retrieval supports applications like photo search, e-commerce, and digital asset management. It also underpins creative tools, where users can provide textual prompts to discover visual inspiration or supply images to find related written material. Cross-modal retrieval demonstrates how merging vision and language not only improves understanding, but also enables flexible navigation of large information spaces. It is a clear example of how multimodal AI bridges the gap between human expression and machine search, offering intuitive ways to find, classify, and connect content across different formats. Zero-shot capabilities illustrate how vision language models generalize beyond their training data. Because these models are trained to align visual and textual embeddings, they can perform tasks without explicit task-specific fine-tuning. For example, a model trained broadly on image caption pairs might still be able to answer novel questions about unseen objects, or generate descriptions for images in unfamiliar contexts. This is possible because the shared embedding space allows flexible connections between words and images. Zero-shot performance is powerful because it reduces the cost and time associated with creating labeled datasets for every possible use case. However, It also introduces risks, since the model may attempt to answer confidently even when its knowledge is incomplete. Zero-shot success highlights the promise of vision-language systems, but it also underscores the need for careful evaluation and oversight to ensure reliability when models operate in uncharted territory. Evaluating grounding in vision-language systems requires specialized metrics. Accuracy is often measured by whether the model identifies the correct object or region referenced in text. For example, if asked to highlight "the man wearing a hat," success is measured by whether the system selects the right figure. Benchmarks such as RefCoco provide structured tasks for testing grounding performance. Evaluation goes beyond correctness, however, to include robustness. A strong system must handle diverse phrasing, unusual images, or overlapping references. For instance, it should correctly distinguish between the dog next to the boy and the boy next to the dog, even though the visual elements are the same. Evaluating grounding ensures that systems are not only capable of linking text to visuals in controlled conditions, but also resilient in real-world complexity. These evaluations are crucial for ensuring that grounding is trustworthy in applications where precision matters. Applications of vision-language models in safety contexts are becoming increasingly important. Content moderation is a prime example. A system must not only detect prohibited words, but also recognize when those words are tied to unsafe imagery. For example, identifying violent or harmful visual content becomes far more effective when combined with textual interpretation. Vision language models can also support fraud detection by analyzing documents that include both images and text, flagging inconsistencies or suspicious patterns. In security context, they can detect sensitive materials by cross-referencing visual and textual cues. These applications show how multimodality enhances safety, offering more comprehensive oversight than text or vision alone. However, they also highlight the responsibility of designers to build systems that enforce safety fairly and accurately, avoiding overreach while still preventing harm. Accessibility is one of the most human-centered benefits of vision language models. Captioning tools powered by these models allow visually impaired users to access content that was once inaccessible. Instead of encountering silent images on the web, users receive descriptive captions that communicate not only what is depicted, but sometimes even the emotional or contextual nuance of the scene. For example, a caption might say, "A child smiling while holding a balloon at a birthday party," giving a sense of joy and context that goes beyond raw objects. Accessibility applications demonstrate how multimodal AI can serve inclusion, helping technology meet the needs of all users rather than only those without disabilities. This is a profound reminder that technological progress is measured not just by efficiency or scale, but by its capacity to broaden participation and enhance quality of life for diverse populations. The challenges of scale in vision language systems cannot be underestimated. Training these models requires enormous datasets of image-text pairs, often numbering in the hundreds of millions or more. Collecting, cleaning, and curating such datasets is resource-intensive and fraught with complexity, including copyright, privacy, and ethical considerations. The computational costs are also immense, demanding powerful GPUs or specialized hardware that consumes significant energy. Scale brings power, but it also introduces risks, such as embedding societal biases present in large-scale internet data. Organizations must therefore balance the pursuit of capability with the responsibility of scale, ensuring that training practices are sustainable and ethically sound. These challenges remind us that technical breakthroughs carry social and environmental costs that must be managed as carefully as the systems themselves. Latency and cost considerations also affect the deployment of vision language models in production environments. Multimodal processing requires more computation than text-only tasks, as images must be encoded into embeddings before they can be integrated with language. This makes inference slower and more expensive. For consumer-facing applications such as search engines or mobile assistants, high latency can undermine usability, while high cost can limit scalability. Organizations must design workflows that optimize speed and efficiency, perhaps by caching embeddings, pruning unnecessary computation, or applying compression techniques. Balancing performance with affordability is essential for making vision-language systems practical at scale. These trade-offs are not merely technical. They shape who has access to multimodal AI and how widely it can be deployed. Affordability and efficiency ensure that these systems do not remain confined to well-funded labs but become tools available across industries and contexts. Ethical considerations are deeply entwined with vision-language systems. Grounding decisions, for example, may encode cultural assumptions or subjective perspectives. A captioning system might describe an image as a woman cooking dinner, but another might say a person standing near a stove, revealing how choices in description reflect cultural and social biases. Similarly, VQA systems may inadvertently reinforce stereotypes if trained on biased datasets. These ethical concerns are not simply technical problems. They require careful reflection on whose perspectives are embedded in the data and how outputs are presented. Organizations must confront these challenges openly, developing methods for reducing bias, communicating uncertainty, and ensuring inclusivity. Without such efforts, vision-language systems risk reinforcing inequities rather than democratizing access to visual information. Ethics must be seen as a central design criterion, not an afterthought. Research is expanding beyond still images into video language models, which extend multimodal reasoning into temporal domains. Instead of analyzing a single snapshot, these systems process sequences of frames, linking them to textual descriptions. This allows models to capture dynamic events, such as a person walking across the street while holding an umbrella. Video language models are particularly promising for applications like sports analytics, surveillance, or education, where sequences matter more than single frames. They require not only visual recognition, but also temporal reasoning, integrating the flow of time into multimodal understanding. This frontier highlights how quickly multimodal AI is advancing. What began with captions for static images is evolving toward comprehensive systems that can interpret and describe the dynamic, multimodal fabric of everyday life. Cross-language capabilities extend the reach of vision-language systems to global audiences. By supporting multilingual captioning and VQA, these systems ensure that users around the world can access and query visual information in their own languages. A photograph could be described in English, Spanish, or Mandarin, broadening accessibility and inclusivity. This capability is essential in a connected world where information must cross linguistic boundaries. Multilingual multimodal AI also supports cross-cultural research, education, and communication. However, it introduces additional challenges, as models must handle the complexity of multiple languages alongside the already difficult task of multimodal reasoning. Achieving this goal requires diverse training datasets and careful evaluation, but the payoff is enormous. Systems that democratize access to visual information globally, not just in English-dominant contexts. Integration with agents demonstrates the broader role of vision-language models in intelligent systems. Agents that plan, reason, and act in the world need perception, and vision-language models provide that perceptual grounding. For example, a household robot might use a vision-language model to interpret a command like, "Pick up the red book on the table," grounding the words in objects it sees. A research agent might combine VQA with retrieval, answering complex queries about scientific diagrams. Integration with agents shows how vision-language systems move from passive description toward active participation, enabling AI to see, understand, and act in coordinated ways. This integration foreshadows a future where AI is not limited to words but becomes a multimodal collaborator, capable of perceiving the world and engaging with it meaningfully. The future outlook for vision-language systems points toward even richer modalities, including 3D and immersive environments. As virtual and augmented reality expand, I will need to interpret and describe not just flat images but spatial, interactive worlds. Vision language models will evolve into multimodal systems that integrate sight, sound, text, and spatial awareness, enabling experiences where AI guides users through immersive spaces. For example, a model could describe a virtual museum exhibit in natural language, or answer questions about the layout of a three-dimensional structure. These future capabilities extend the principles of grounding, captioning, and VQA into new dimensions, making AI an active participant in both digital and physical environments. The trajectory is clear. Vision language models are not endpoints, but stepping stones to broader, more immersive AI systems. As we transition to the next discussion, it is important to see how document intelligence builds directly on the capabilities of vision language systems. Many documents are multimodal, combining text, tables, charts, and diagrams. The ability to interpret and reason across these elements is an extension of the same grounding, captioning, and VQA principles applied in vision language models. Document intelligence leverages these multimodal foundations to make complex, structured information accessible and actionable. This progression shows how vision language systems are not isolated technologies, but part of a continuum that leads toward richer, more comprehensive forms of AI capable of handling the full diversity of human information. Vision language models therefore represent a significant step in the evolution of artificial intelligence. By integrating vision and text, they extend system capabilities beyond language into richer domains of meaning. Their core tasks, grounding, captioning, and visual question answering, demonstrate how AI can connect words to objects, describe images in natural language, and answer queries about visual content. Their applications range from accessibility and education to safety and enterprise knowledge management. Yet they also raise important challenges of bias, scale, and ethics that must be addressed responsibly. As research expands into video, 3D, and multilingual domains, vision language models will continue to broaden the horizon of what AI can perceive and express. They are not just tools for description but engines for understanding, enabling AI to participate more fully in the multimodal nature of human knowledge and communication. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.